everybody.
Today we are going to discuss about some standard examples on two-dimensional probability distribution, especially two-dimensional continuous probability distribution. Some standard two-dimensional continuous probability distribution. To begin with, we shall discuss this distribution known as rectangular or uniform distribution. Rectangular or uniform distribution. What is this? It says that the spectrum of the distribution can be a rectangular region. This kind of rectangular region may be in two-dimensional plane. Suppose this kind of rectangular region, and this rectangular region are actually bounded uh, this kind of interval, that a less than x less than b, and in along y-axis it is bounded by this kind of interval, like c over here, c less than y less than d. So this is the interval c less than y less than d. So if a point, this kind of point, if you consider this kind of point, and if it is the value of the two-dimensional random variable xy, then we can say that the point x comma y, or the random variable, two-dimensional random variable x comma y, lies within this kind of rectangular region. And within this kind of rectangular region, for such choice of the values of x and y, the density function has this kind of expression 1 by b minus a divided by d minus c. What is b minus a? B minus a is actually equal to the length of this interval along x-axis, and d minus c, this is the d minus c, this is the length along y-axis. So you can say altogether this denominator b minus a into d minus c, b minus a into d minus c is actually the area of this rectangular region. And what is the value of the function f outside this rectangular region? Outside, that means elsewhere, the value of the rectangular region is equal to 0. And this is known as rectangular or uniform distribution over a rectangle. And sometimes in general we consider rectangular region on any arbitrary set. Maybe this is a set having area is equal to r, and in that case the density function can be defined in this way, that this f of x comma y, this is equal to 1 by r whenever this point x comma y belongs to this set, and this set is also denoted by the same notation r, because we do not have any confusion, because over here this is a real number, maybe 2 square unit or 3 square unit, and over here this is a set. So from the notation it is clear that there is no such confusion at all. So this is the this is equal to the density function, and this would be is equal to 0 elsewhere. So elsewhere this is equal to 0. In this fashion we can define an uniform distribution. Remember, it is not rectangular, because over here this region R is not rectangle, but we call it uniform distribution over this kind of any arbitrary region R, and this is the corresponding density function of the rectangular region, or any arbitrary region R. Okay. So over here I discussed this one, over any arbitrary region R. This is the definition of the density function. And on this kind of arbitrary region R, what would be the probability that capital X comma Y capital X comma capital Y belongs to this region R. What would be the probability of this event? What would be the probability of this event? We can also consider R dash over here or R prime. What is R prime? Suppose this is the total spectrum, and maybe this area is equal to R, and we have a subset or a event represented by R prime. So if xy belongs to this kind of region R prime, then what is its probability? We need to integrate the density function over this region R prime, and as because the value of the density function is equal to 1 by R, so in place of f of x, in place of this f of x, we can put 1 by R, and then we can integrate. Then after integration, we will have simply R prime divided by R. So you see, computation of probability becomes very much easy over here. Just you need to divide the region R prime by the area of the region R. R prime by R, that would be equal to the probability that xy lies in this type of arbitrary region R prime. Okay, so by this kind of formula, we shall in future compute probability of the point which follows an uniform distribution. Now the question is that what kind of in what kind of cases we obtain this uniform distribution. Mostly you see in case of one-dimensional distribution, we discussed that if in an interval, if we randomly choose a point, then that point forms a rectangular distribution. Say if we consider this kind of interval, maybe an open interval or a closed interval, whatever you consider. Let us, for the sake of discussion, consider open interval, because in case of continuous distribution, it is customary to choose the open intervals as the spectrum. So if this is the open interval A and this is the open interval B, and if you consider any random point, this kind of point may be equal to P, then this much distance from any endpoint, either from the left endpoint or from the right endpoint, this kind of random variable capital X. If we define a random variable capital X denoting the distance of the point P from the point A, in that case, this kind of random variable capital X will follow an uniform distribution over the interval A comma B. And the same case arises if we consider two-dimensional plane. If for the starting point we can consider any rectangular region, and if you consider any arbitrary point on this region, then their coordinates capital X and capital Y. These two coordinates will follow a two-dimensional uniform distribution. Even in case of any arbitrary region as well, if we consider any arbitrary region and choose any point P, then its coordinates capital X and capital Y, these two coordinates will follow the uniform distribution over this kind of region. Let us call it R. So if any point is chosen arbitrarily on a straight line or on a segment of the surface, in that case, this kind of points follow uniform distributions. Okay, let's make it clear by considering one or two examples over here. Consider this kind of example. This is known as Buffon's needle problem. Buffon's needle problem. What does it say? It has a little printing mistake. It is written as that we have a vertical board. Not vertical, it would be horizontal. If you consider the latest version of this book, you will find that the rectification has been written properly. Okay. So we actually have a horizontal board, not vertical board, and on that board we draw few parallel horizontal lines. Of course, the lines would be horizontal, and we consider uh, parallel lines at constant distance b apart. Hmm. How can we draw this one? We can have this type of scenario. Suppose we have a rectangular, maybe this kind of region, hmm, and it is suppose it is a boat, we kept horizontally, and on this kind of suppose you can consider a table, this kind of table, hmm, this kind of table over this kind of table. You can consider this table as a on the upper surface of the table as this kind of horizontal, as a horizontal board, and on this kind of horizontal board we have some horizontal lines, this kind of horizontal lines, maybe 2 or 3 or 4 lines, and there what would be the distance? It says that this distance, the distance between these two lines, this distance is equal to b. So this line, the distance between these lines are always equal to b. Okay, and on this kind of surface, what we need to do on this kind of surface? It says that a needle is thrown, a needle of length a, is thrown at random. Mind it, it is thrown at random on the board. All right. A needle of length a is less than b, it is thrown at random on the board. What we need to find? We need to find the probability that it will intersect one of the lines. We need to find the probability that it will intersect one of the lines. And for the sake of convenience, let us draw this plane in this kind of two-dimensional surface. So, say this is a plane. Suppose this is the plane, and there we have few horizontal lines like this, drawn b apart. Okay, and over here, this much distance is equal to b. This much distance is equal to b. This distance is b. This distance is also equal to b, and so on. This distance is equal to b, etc. Okay. Now a needle is thrown, and if a needle is thrown on the board, it will ultimately lie either in this way, or in this fashion, or maybe in this fashion. It may also lie in this way. It doesn't matter. The orientation is not a fact. Over here, it may lie in this fashion. It may lie in this fashion. It may lie in this fashion. I'm not talking about the orientation. I'm just saying that either the needle may intersect one straight line, or it may not intersect this straight line at all. That means what could be the possible cases when it intersects? It may intersect in this fashion. All right, and if it is not intersecting at all, the needle will be situated like this, and if it is the length of the needle is equal to small a as per the question. And now let us define two random variables. One is this distance, capital X, let us call it capital X, and another is this much distance from immediate lower straight line. Let me draw this one by different color. Say this is y. Okay, this distance is equal to y, this much distance. All right, this much distance is equal to y. Now you see over here, if I made a mistake, just a minute, I made a mistake, I think. Over here, let us not write this as capital X. Rather, let us consider let us consider this angle. Let us consider this angle is equal to the angle capital X. All right. So let us consider this angle is equal to the angle capital X. Now you see this horizontal distance. This horizontal distance is equal to capital X cos of, sorry, not capital X. I would rather say this horizontal distance would be A cos of X. Okay, and this much distance. This is the base and this is the perpendicular. This much distance would be is equal to A sine of capital X. Okay, and you see if a needle intersects at all, it will intersect in this fashion, and you see in that case this value, this would be the value of y. This value must be less than this much horizontal, this much length of the perpendicular. This is the base of the triangle and this is the perpendicular. Okay, so this is the perpendicular distance. So we can say over here this y would be less than a sine of x. Why? Because a sine of x is actually equal to the base of the perpendicular. Let me draw this one over here in a fresh fashion. I think it would make it a bit clear. Now you see, if this is the straight line, if you consider this kind of horizontal straight line, suppose this horizontal straight line is cutting over here, and in that case, you see this would be the distance y, and this would be our a sine of x. Why? Because this angle is equal to x and this length is equal to small a. As per the question, a is the length of the needle. Alright. Therefore, if this needle intersects the horizontal line at all, if this needle intersects the horizontal line at all in this fashion, intersects over here, in that case, if it intersects the horizontal line at all, in that case, what we should have? We should have this result that y is less than a sine of capital X. All right, and from this region, it is clear that the maximum value of y. You see, this is the length y. So maximum value of y would be is equal to capital would be is equal to small b. Because you see, if this end intersects over here, it crosses this region, in that case we can measure with respect to this line. We can measure everything with respect to this horizontal line. We are measuring over here with respect to this kind of horizontal line, just to the line below the middle. All right, so we can say that the spectrum of y would be 0 less than y less than b. And what would be the spectrum of x? You see over here, x is the angle. X is this much angle over here. X is this much angle, and therefore we can say that it may be at most is equal to 180 degree. So we can say that 0 less than x less than pi. Okay, 0 less than x less than pi would be the spectrum of capital X, So the spectrum of the joint distribution of x comma y can be written in this way. So we can say that over here this joint random variable has this kind of spectrum, and you observe that this actually this spectrum represents a rectangular region in two-dimensional plane. So if we can draw the spectrum, what would be the spectrum? You see, in two-dimensional plane the spectrum would look like this. Say these are the two axes, and suppose this is the x-axis, this is y-axis, and 0. What was the spectrum? The spectrum was that 0 less than x less than pi, and 0 less than y less than b. So if we consider a straight line, say this kind of straight line parallel to y-axis, and suppose this value is equal to pi, therefore we can say that 0 less than x less than pi will represent this type of interval. Okay, and similarly over here we could consider a straight line parallel to x-axis, and suppose this over here this is y is equal to b, therefore this region would be the region that 0 less than b less than y. Therefore this is the rectangular region, and in this kind of rectangular region, as I discussed earlier, what is the required event? This is the required event, that y less than a sine x. Okay, so the required event is that y less than a sine of capital X, and of course y is greater than 0 because it was representing length. So 0 less than y less than a sine of x, 0 less than y less than a sine of x, and as per the question this a is less than b. So what is the region representing this type of inequality? Remember, the upper limit is a sine of x. So at most a sine of x, we first need to draw the curve of a sine of x. What would be a sine of x? The curve would look like this kind of curve, a sine of x, this kind of curve, and over here this is the maximum height of that curve, and that height would be is equal to a. Remember, we are given that a is strictly less than b, therefore this curve cannot intersect the point y is equal to b over here. Okay, so this is the region, on which we shall need to integrate. Why? Because over here the point x comma y, x is also a random angle, and y is also a random length or random variable, you can say randomly chosen. Therefore x and y together, they will represent a rectangular region, and in that case what would be the density function? Rectangular region, over here the total spectrum is given by this type of this kind of inequality. And what would be the area of this region? Area R is equal to, you see, and the length is equal to pi, and over here this length is equal to b. So R would be is equal to pi into b. Therefore we can say that density function would be is equal to 1 by R, that is 1 by pi into b, when x and y both lie in this region, and of course 0 otherwise. So this is R, and if this is the area of interest, then how to find out the region R prime? How to find out the region R prime? you see, in order to find the region R prime, that is actually the shaded region over here, we just need to integrate this a sine of x. We just need to integrate this a sine of x. Integral a sine of x in between, what is the lower limit of x? X is equal to 0 to x is equal to pi, in between 0 to pi. So just integrate in between 0 and pi. Ultimately, you will get the value of this r prime. Okay. So what is r prime? R prime is equal to, if you integrate it, you will get is equal to twice a. Clear? So the required probability, or you can say the probability that this relation is satisfied. This is the required probability. What would be the required probability? Required probability would be is equal to r prime divided by r. That is equal to twice a divided by r, means pi into b. So in this way, you can find out the probability of the required event. You need to identify this event by this kind of picture, and remember, please always draw this kind of picture in each and every problem. Try to draw this kind of picture in each and every problem, because it will make your concept clear. Not only it will make your concept clear, but even in examination, it would be much more easier for the teacher to understand what are you doing or what are you writing over there. So in a two-dimensional distribution, if you have this kind of any kind of problem, please try to draw the proper picture so that it becomes much more easier to understand to you as well as to the examiner or the teacher. Okay. Now see, is it clear to you, everybody?
Yes, sir.
Any kind of question? No question. So you can go through this type, and this type of similar problems are also there. You can go through, say, this kind of problem number 2, 3, 4, etc. And you just need to understand how did we get this type of inequalities, because everything is about these inequalities and shading a particular region. And in that case, you can identify your particular region on which you need to integrate it, so that you can find out this region R prime. Otherwise, the problems are much more easier. All right. So these are all about uniform distribution. Now let's come to the next distribution, that is called the binomial. Bivariate normal distribution. Bivariate normal distribution. What is this? The bivariate normal distribution. You see, we already know the normal distribution in case of single variable. Let me make it a bit larger. We have this type of density function. If if we have a function of single variable, a probability distribution of a function of single variable, in that case, f of x, the density function of a normal distribution, normal m comma sigma distribution, is generally written in this way: 1 by root over twice by sigma. In place of sigma, I have written sigma x. This is one parameter. Sigma x is always greater than 0, and multiplied by e to the power of half minus half into x minus mx divided by sigma x whole square. Let me make it a bit larger, something like this: x minus mx divided by sigma x whole square. So this was the density function of normal distribution for a function of, in case of single random variable. And it can be proved that this expression x minus mx divided by sigma x follows a standard normal distribution, or you can say that if we designate it by x star, then corresponding density function would be the density function of the normal distribution, like this: 1 by root over twice by sigma, sorry, not sigma, 1 by root over twice pi, because in case of standard normal distribution, sigma becomes is equal to 0, e to the power of minus half x star square, corresponding m becomes also is equal to 0. And you have already I discussed in the previous chapter that this m is nothing but is equal to the mean of the distribution, and this sigma is actually is equal to the standard deviation of the distribution. Over here, m x and sigma x can be treated as a parameter, but later on we can find that these mx and m sigma x are actually mean and standard deviation of the random variable capital X. Now, we extend this one. We extend this idea, and the bivariate normal distribution is defined in this way. And remember, over here, in case of bivariate normal distribution, we have 5 parameters. And what are the parameters? Let me tell you one by one. Just like mx, we have my, m suffix x, we have m suffix y. Similar to sigma suffix x, we have sigma suffix y. And there is one more extra parameter that is called rho. And what is the physical meaning of this parameter rho? I shall discuss them in the subsequent part of this chapter, but not today. All right. So, what is the definition? The definition says that definition of this density function, it would be is equal to 1 by 1, not 1 by root over twice pi. Remember, just multiply similar expressions for x and y. So, if we have two different 1 by root over twice pi, we shall have simply twice pi corresponding to sigma x. We have sigma x, and along with that we have one more sigma y, and this is the extra contribution that would be equal to root over of 1 by root over of 1 minus rho square multiplied by e to the power, and the exponent is very large. Let me just copy this one, and for your convenience, let me paste it over here. This is the and let me minimize this one a bit. Yes, and this is the exponent. This is the exponent portion, e to the power of this much. What is this? 1 by with this negative sign, 1 by 2 1 minus rho square, and within this bracket you can identify the similarity. In case of single random variables, we had 1 by 2 minus 1 by 2 into x minus ns by sigma x whole square. Mind it, square is there. So exactly similar expression is there, x minus mx divided by sigma x whole square, and same kind of expression is there for y minus my divided by sigma y whole square, and the third term is there, minus 1 by twice rho into this factor x minus ms by sigma x multiplied by this factor y minus my by sigma y. Remember, we are not considering any square over it. So this is the exponent part. So it is a bit very large and heavy portion. Okay, and over here the parameters are, these are the parameters. One is this mx, then my. Both of them may be positive, may be negative. Then we have the third parameter sigma x and the fourth parameter sigma y. Both of them must be positive. And this parameter rho, it varies in between 0 and it varies in between -1 and +1. So we can say that this m of x may become anything from -infinity less than mx to +infinity. Okay. So similarly for m of y, and then sigma x would be greater than 0, sigma y would be greater than 0, and -1 less than rho less than 1. That is the restriction on rho. And you see, rho cannot take this value. Rho is equal to +1 and -1, at least as per the definition. And if rho becomes is equal to 0, particularly a special case when rho becomes is equal to 0. In that case, in the exponent, this middle term would not appear. This middle term would not appear if rho becomes is equal to 0. So just remove this expression. So in the special case, if rho becomes is equal to 0, then what we observe? Then we observe that f of x comma y, this joint density function, can be written in this way. And you see, you can observe that this it can be decomposed into two parts. One is a purely function of x. Let me write it in a larger fashion: x minus mx 1 by root over of y by into sigma x e to the power of half into x minus mx by sigma x whole square. And similarly over here, same type of expression involving y, 1 by root over y by into sigma y into x minus e to the power of minus half x minus my divided by sigma y whole square. So you see, this is a function, purely a function of x and purely a function of y. And I told you earlier that two random variables, capital X and capital Y, are independent if and only if the probability distribution function, in case of distribution function, if and only if the probability distribution function can be written as the product of a function of x alone and the product of a function of y alone. And over here, the same result is true about the probability density function as well. So over here, you observe that this joint probability density function has been represented as a function of x and a function of y. This is a function of x alone and this is a function of y alone. And we are going to show that this is nothing but is equal to the marginal density function of x and this is the marginal density function of y. Got it? We are just going to show, then these are some standard questions in the examination to find the marginal density function of x and the marginal density function of y from this joint density function in case of bivariate normal distribution. Okay, so let us go through this problem. This is the density function of the bivariate normal distribution. And not probably this is truncated. It may appear that this is truncated, but you see over here, this is the total exponent written. Just for your clear identification, I made a bit larger magnification. Anyway, so this is the density function of the bivariate normal distribution, and how to find out the marginal density function. We just need to integrate the joint density function with respect to y. So just now we put this large expression over here within this bracket, then this large expression will have to be integrated with respect to y. And over here, mind it, the expression involving x will be treated as a constant quantity, or at best you can consider that this x can be treated as a parameter of the integration. So for the sake of simplicity, we are taking this expression inside the bracket, this x minus mx by sigma x. For simplicity, let us designate by x prime, and similarly the expression within bracket, the similar expression within bracket for y. Okay, let me show it over here. This expression y minus my divided by sigma y. Let us consider this as y prime. Okay, so considering this kind of transformation, then you see we do not need to write this dx is equal to sigma x into dx, because over here no more dx is there. We are integrating with respect to y. So it is this line is only the relevant line. dy is equal to sigma y. If we just consider y prime is equal to y minus my divided by sigma y, then dy is equal to sigma y into dy prime. Now consider this expression within braces. This is the expression. Let me make it a bit smaller. this one. This is the expression within bracket. So this is actually our x prime. This is also x prime. This is y prime. This is y prime. So what we shall have? We shall have x prime square minus 2 x prime into y prime plus y prime square. Something like this one. Now you see this expression can be further manipulated, and we are trying to express out of this expression we are trying to extract some square perfect square expression involving y prime. So if we just adjust this term minus rho square x prime square, then add this one minus rho plus rho square x prime square, we can have this type of perfect square, and this remaining term can be written in this way, taking x prime square as common quantity. Okay, and similarly this is a similar step for x prime. In order that would be helpful in order to compute the marginal density function of y. Over here we are just computing the marginal density function of x. Similar computation can be performed in order to find the marginal density function of y. So this much would be helpful in order to compute the marginal density function of y. Therefore, in place of this exponent, in place of this type of expression, we are just putting this expression, and this in the denominator 1 by 2 into 1 minus rho square was there, so I am keeping this one as it is. Now this, you see, this dy can be written as this, as I told you, this dy can be written as sigma y into dy prime. And you see what was the range of y? The range of y was from minus infinity to plus infinity. So you see y prime would also have the same type of range from minus infinity to plus infinity, because this m of y, this is finite quantity, and this sigma y is positive. I told you earlier that this my is always greater than minus infinity, less than plus infinity. So it cannot take any infinite value. It is always finite. My is finite, and this sigma y is greater than 0. And therefore, we can say that the range of y prime would be from minus infinity to plus infinity. And now just a simple calculation. You see over here in the exponent 1 minus rho square, and this two will get cancelled. So we shall have e to the power of minus x prime square by 2 minus this square divided by 2 into 1 minus rho square, something like that. And now what to do? We are just making separate this expression, this exponent, e to the power of minus x prime square by 2. So we are keeping this separate. Along with that, we are just decomposing this first term as well. Over here, you see 1 by root over of twice pi sigma x is kept separate, and the remaining term 1 by root over of twice pi into sigma y would be there, but the sigma y is actually getting cancelled with the sigma y, so no more sigma y comes over here. Only this root over of 1 minus rho square will be present. Okay, and now you see over here, you can now consider this expression as sigma. You can consider this expression root over of 1 minus rho square as sigma, simply a sigma. So it would be 1 by root over of twice pi sigma e to the power of minus, and you see this expression can be considered to be is equal to a parameter small m. This rho into x prime, this can be considered to be equal to a parameter small m. So what we have, 1 by root over of twice pi sigma e to the power of minus 2 minus this y prime minus m whole square divided by 2 sigma square. You can arrange it in this fashion. You see, let me arrange it for you. Say 1 by 2 only. 1 by 2 into then this one over here. Forget about this 2. So you can extract this sigma inside this bracket. So you can write it in this way: minus half into y prime minus n by sigma whole square. So this is exactly similar to the exactly similar to a normal distribution with parameter m and sigma. And we know that this is the density function of such normal distribution, and the integral of this kind of density function is always equal to 1. We know that the total integral on a density function is always equal to 1, therefore this value is always equal to 1. So I'm just putting over here 1, and the remaining term we have outside this integral. And that can be further elaborately written in this way. You see that it is equal to 1 by 2 power twice by sigma x into e to the power of minus half x prime square. What is x prime? X prime is equal to x minus mx by sigma x. So this is the marginal density function of x. I told you that this expression is the marginal density function of x, and by similar fashion, by similar computation, we can say that this over here, this is the marginal density function of y. Okay, so if x, these are the marginal density function of y, so we can say over here, if rho is equal to 0, then this capital X and capital Y are independent random variables. But if rho is not equal to 0, then we cannot say that this capital X and capital Y are independent random variables. Then in that case, we need to further study what would be the what kind of expression might become an independent variable, and in order to find this answer, we'll have to study the conditional distribution, a new kind of distribution that I shall discuss in the next class. Okay, so this much I wanted to discuss in this class. So that's all for this lecture. Thank you for being with us.